Project 8, what we're going to do is we're going to come up with a few methods of determining pi, trying to find a ratio between the circumference and diameter of circles, and we're going to do that by using different circular objects, different round objects. We're also going to look at relationships between the circumference and the area of circles. And so for this first part, if we were trying to find what is the ratio, what is that scale factor, that number that we would multiply to find the relationship between the diameter of a circle and the circumference of a circle, what we've done is I took several round objects that I have. Some are machined, some have just been cut by wood, some are just manufactured that way, so that we can try and get an average. And so I picked these objects here, these 8 objects. One is a derby cover from a motorcycle that keeps all the oil in. One is a large spool that's used for running cable underground. So one of those large ones that they can turn into tabletops you see on the back of trucks. A soup can, a pizza cooking stone, a beer bottle, a can of wood urethane sealant, a small spool, and one that would just be like for running wire inside of a building, and a 55-gallon drum that we had out here. And all of these measurements are in inches. So if you look, the circumference of each varies. I tried to find objects that were not very similar to each other, like a vegetable can and a soup can or something. So that way we can get a wider range, larger objects, smaller objects, and try to come up with an average. So this was the circumference of each. And you can do this by taking a piece of string and attaching it around the object and then laying it out against a ruler, a yardstick, etc. What I happen to have is, because we do surveying on the land, is actual tape, large tape measures that could go around this. So we got pretty accurate, down to a couple decimal places in some things based on the increments. And these are the circumferences we came up with. And then what we did is we ran the diameter of each. And the diameter of each, again, you could take a piece of string, or if the object is small enough, you could use a ruler. In this case, I used that tape for a number of the larger objects, like the large spool, the 55-gallon drum, so I used the tape wheel for those. For some of the smaller ones, I used a pair of calipers, and so that gave us quite a bit of precision on some of these, because we were able to measure using industrial calipers. So looking at that, just automatically it's hard to see a relationship. All of these seem to be about a third of what the circumference is. If you look at the diameters, multiplying them by 3 roughly gives you this value over here. So what we did in the column is we just take the circumference divided by the diameter. And in Excel, of course, you can just enter the formula once and drag it. And we get all these values of 3.17, 3.15, 189, 3.1489, 3.15789, etc. Now, they're all very close. They're all 3.1 something. That second digit, the hundredths place, seems to be the variance. Now, this could be the precision of our measuring, the tools that we were using. The fact that when a wooden spool is cut, they're not too worried about it being perfectly round, just round enough to be able to roll it on the ground, things like that. So, based on how accurate they were in creating it and how round it actually needed to be, we have different measurements. Now, the last column, or excuse me, the last row is the average of all of those. So we have 3.15987. Now, this isn't exact. I mean, this is an average of just household items and stuff laying around the yard. But we know that pi would be 3.14159265, etc. And so this gets us kind of close. Okay, so there are methods that they used in the past, as far as like taking stones and arranging the stones into a circle and then counting the number of stones going across, and doing that for diameter, number of stones that were in the circumference, etc. And so there were cruder methods. So this actually gets us probably a little bit closer, because some of these things are industrially made. They're going to be a bit more round than you know, say just taking pebbles or marbles and putting them on the ground and arranging them into some sort of circular fashion. Okay, so the questions would be, of course, what do you know about the numbers in the last column? Well, of course, all of these are relatively close. It's the hundredths place that is off, and there's, you know, only so much variance: 3, 4, 7, 5, 4, etc. The average, of course, gets us somewhat close to pi. It's a little bit over. Again, the precision of our measuring, how round the object actually is based on how round it needed to be for its purpose. You know, nobody really measures a small spool and things like that. Now, the questions we could ask the kids, or the students I should say, is why did we use the ratio of circumference to diameter for several objects instead of just picking one? Well, if we just did one, let's say the soup can, we would get 3.1894. Well, this is going to put us at the very high end of pi if we're trying to come up with a good average. And if we picked, let's say, oh, let me turn that back on, the small spool, well, this could put us pretty much right on it, almost right on top of it, just a little high. But by taking several objects and coming up with an average, that's going to get us closer than just randomly picking one and saying, okay, I believe this is going to give us the best value of pi, or this one is. So the more objects we take, the more things that are in our sample space, the closer we're going to get. If I did more than 8 objects, possibly did 100 objects, 200 objects, and we started focusing on things that were precision manufactured, well then of course we would get a closer number to pi. Okay, were any of the ratios in the last column not close to 3.14, and if not, explain what might have happened? Well, things like this: the derby cover 3.17, the soup can 3.18. Those weren't close. Now, varying reasons. Again, the soup can may have been dropped, and it may be that, you know, it's a little bit out of round. It doesn't need to be perfectly round, but they're pretty close. It may have gotten bumped in transit, and it just so happens that where we measured across the top of the can was a little bit wider at that point. If we had taken several measurements across the top and then taken an average, we may have gotten something a little bit closer to pi as far as our value. Again, machining tolerances, accuracy, you know, some things just don't need to be perfectly round. So that's why we are going to have some variance where everything is not exactly 3.1415. Describe some situations in which knowing the circumference and how to calculate it would be useful. A basic example, something that we give students all the time, is say that somebody wants to plant a circular garden. Okay, well, if maybe something is large enough that we really can't calculate the circumference, maybe we don't have a tape that long, but we can measure the diameter across. We have an area with a diameter of maybe, you know, 33 1/3 feet. How much fencing would we need to buy in order to enclose that circular garden to keep animals away from it? Okay, just a real basic example. So the kids can come up with some on their own. Okay, so in conclusion, the distance around divided by the distance across is going to give us a value of pi. So therefore, pi is going to be equal to the circumference divided by the diameter. Okay, so that is our ratio. That's how we found it in that last column on the previous worksheet. So the circumference, just by rearranging the formula a little bit, the circumference is just pi times the diameter. So like in the fencing example, if we know the diameter of an object and we need to find out what its circumference is, well then we can multiply it by that ratio pi, that scalar. And if we were doing things in terms of radius, which a lot of geometry classes work more in radius and they rearrange the formula so that they use radius instead of diameter, well then, of course, radius being half of diameter, we would just have to multiply the radius by 2 and then again by pi. Okay, so that would be our factor. Pi is what we can multiply the diameter by, or multiply 2 times radius, same as diameter, in order to find our circumference. Okay, for the second part, we're going to work a bit with area. Now, a long time ago, we didn't have exact numbers of pi. We didn't have good measuring tools. People were still using their arms for such things. But Archimedes was able to discover pi with great accuracy. And, I mean, of course, not out to billions of places or anything like that, but enough for that day that it was a really accurate number. Now, he didn't know exactly what pi was. Okay, now you could take a piece of string and you could wrap it around a circular object, and then you could take that same string and measure the diameter across, and you would see that the diameter is roughly 1/3 of what the circumference was, your distance around the object. And so some people might just argue that it's about 3, or it's a little over 3, something like that. And we looked at that in part 1 just a minute ago. But what he did know is he knew polygons. And so with this program, I'm just going to work with inscribed polygons. But what Archimedes was able to do was take a polygon and inscribe it inside of a circle, and then also circumscribe it about a circle. So let's say in this example we have this triangle here inscribed within the circle. Well, the triangle we can measure, and we can find a radius of it, which is going to be the distance, of course, from the center of the triangle out to the vertice. And of course the radius is going to be the same if I go from A to C, from A to B. In here I have it going from A to B prime, is the one that I called out. And we can measure and we can find area because we know how to find the area of a triangle. And if I circumscribe a triangle about the circle, well, then I can find the area of that triangle. And logic tells us that if I have a triangle inside of a circle and a triangle outside of a circle, and they're contacting, of course, the second triangle, the circumscribed, the circle would be making contact on the sides of it, whereas here on the inside the vertices are contacting it. Well, then the area of the circle has to be somewhere between the area of the small triangle and the area of the large triangle. Now, I did that, and of course you have a huge gap between the two triangles. And so that doesn't tell you much. It leaves it wide open as to what the circle could be. But Archimedes, being a smart man, decided to increase the number of vertices of the polygon, raise the n of the n-gons. And so he put a square inside of a circle and a square on the outside. Well, that gets us closer because, as we learned in sophomore geometry, or freshman for those of you who took it then, the more vertices you have, the more sides you have of your polygon, what does it start to resemble? It starts to resemble a circle. An octagon looks a lot more like a circle than a triangle does. But then again, if I do 20 sides, if I do 100 sides or more, it gets to a point where it's almost indistinguishable because our points are so close that we're not even seeing the actual sides anymore. And that's, of course, just because of the technology we have, or the accuracy of which we do things. So I'm going to show you an example this way, and then I'm going to use some graph paper to show you another way of calculating area. And so in this example, what I did is I set the radius to 1. The radius is variable on this, and if anybody wants this this little program I made, I'll be glad to send it to you. But you can vary the radius. I'll just show you. I can make the radius 1/2 or smaller. I can make the radius of our circle and our polygon all the way up to 5, and of course all of that stuff is variable. It's real easy, but I want to keep it at 1 because it's going to be a little bit easier to work with and easier to understand. But we can prove that the formula that we come up with for area is going to work with any radius that we have, and you know, when we do our shapes and everything, it's going to be constant. Our formula is going to be the same regardless of radius. Okay. Now the number of sides, of course, the smallest number of sides that we can have for a polygon is going to be 3. So that's what I set it for, and I have a triangle on the inside. But this is what I'm going to want to show you. Down here at the bottom, let me loosen that up. Down here at the bottom, what I have is an estimate for pi. Okay, and I'll explain in a minute how we got this estimate, but this number is going to change as we start increasing the sides. Okay, and this has to do with, of course, this is an estimate because we're dealing with the perimeter of the excuse me, with the perimeter of a polygon. So in this case, the perimeter of the triangle, which is measurable, divided by 2 times the radius of the polygon. So right now we're not going to be anywhere close to pi. Why? Well, because if you look at the triangle, if I do 2 times this radius, what's it going to do? That's going to end up somewhere out here. Okay, so our value of pi, it's going to be a little bit off. Right now we're at 2.59 if I do perimeter divided by 2 pi. Okay, and then I have a separate thing where it says that the area of the polygon with 3 sides and radius 1 is going to be this number, this 1.29. Okay, it's another formula which, if you want, I can send all of this. Now these numbers are going to change. Everything will change. Now I have it set up that if I change the radius up top, it's going to change radius here, and as I change the number of sides, our end value, that this is going to increase. These numbers should begin to converge upon the same number. They should start to go in at different rates and approach the same number, the same limit. So we're going to do a quick demonstration of pretty much what Archimedes did, just without the circumscribed polygon. Okay, so let me set this up here so we can get this. Okay, so let's say I increase the number of sides to 4. You can see that the square takes up more space inside of the circle. Our pi increased a little bit that we have here, and the area of the polygon, okay, 4 sides, radius 1 is going to be 2. Now this is just simple math. If we're given the radius, or we're given an apothem, or anything like that, we can find the area of a polygon. Okay, and so that's all it's doing. I can increase it to 5 sides, 6 sides, 7, 8, and you notice that by the time that we get to an octagon, our value of pi has now gone over 3. Okay, our estimate, and remember that was just the perimeter divided by 2 times r. Okay, going back to the first part of this lesson, how do we do that for a circle? Well, it was circumference divided by 2 times r is going to give us pi, our pi value. Well, the closer this gets to looking like a circle, the closer the perimeter is going to be to the circumference of the circle. Okay, we use circumference when we talk about the distance of, or the distance around a circle, but we use the word perimeter when we're dealing with polygons, because what we're doing is we're adding up all of the sides. Okay, but the perimeter and the circumference are going to start approaching the same number the more ends we have, the more number of vertices that we have. Okay, so the formulas are going to be real similar. If as n approaches infinity, the perimeter becomes the circumference. Okay, and so the area of the polygon with 8 sides, radius 1, it's using the radius, and it's just trigonometry. Okay, every polygon, every regular polygon is just made up of triangles. And so that's all this formula is doing, is finding the area based on that. Okay, as I increase numbers, you notice that as the vertices increase, the sides increase. What are we doing? We're beginning to get it more like a circle. Now, of course, it would be an infinite number of points before it actually became a circle, but what level of precision are we looking for? How close are we looking at getting pi? So I'm going to fast forward a little. We notice that even at just 25 sides, okay, our value of pi is at 3.133. We're getting close to the 3.14159, etc. Now, from what I read, Archimedes did this to 96. So I believe he did a circumscribed and inscribed polygons around a circle with 96 sides. Well, you notice, even at just the 96 that he probably stopped at, we're already at an estimated value of 3.1410. So only thing that's off is our 10,000ths place. We're good on the first three places after the decimal. Our 10,000ths is just half off. Instead of being a 5, it's at 0. Okay, the area of the polygon with 96 sides and radius 1 is going to be 3.139, which is very close to 3.14. Okay, so Archimedes got very close with this, a very close approximation of pi with only 96 sides. Okay, again, the polygon, as the number of sides and vertices increase, it's going to resemble a circumference, and so the area is going to be close. So as we're doing our division, we're going to get a number close to pi. Now I set this up for us to just keep going, and I didn't want to lock up the computer, so I didn't do too many sides. I figured that if I did too many, that the software would probably freeze on me. But I want you to pay attention to something as I increase these numbers. And let's zoom in on that. Is that as the number of sides increase, currently we're at 511, we're very, very close. This should be 3.14159. Well, we're at 3.14157. Okay, as the number of sides increase, what's going to happen? These numbers are going to be locked in. This is going to hit 9 and stay, and then the numbers after it are going to keep changing. And then the next number after 9 is going to lock in, and so on and so forth, and it's going to resemble what we have. Again, because I only put so many sides in, we're not going to get it exact for these first 14, 15 numbers, but watch the numbers as I increase. Okay. Alright, now we didn't get as close as I wanted, but this is very close to the 14159. We're up to 87. Okay, and if you look, that is with 1,000 sides. And so our circle now, because I didn't turn off the feature that numbers all of the vertices, everything is indistinguishable. You can't even see the numbers because I have 1,000 points on the inside. I have a 1,000-sided polygon inside of that circle, inscribed inside of it. Okay, our value that we came up with, not using circumference but using perimeter and radius, is 3.14157. So it's getting closer to our estimated value of pi that we had over here. Alright, if I was to take this higher, if I was to go to 2,000, 3,000, 10,000 sided polygon on the inside, it is going to keep approaching pi from the bottom. Now I say from the bottom because what did we do? We worked with an inscribed polygon. If we had worked with a circumscribed, then we create kind of a squeeze theorem thing. We have a upper value and a lower value, and we would be approaching with the circumscribed one, we would be coming from a greater value down towards pi. With the inscribed, we come from a lower value towards pi, and that would help us, and that's what Archimedes did, because what did we do? We sandwich it. We have a value of area that's greater, we have a value of area that's slightly smaller, and so we know the area of the circles between there, so we start to get a better idea of what the value of pi has to be. Okay, we know the radius, that's a given. The radius is for the inscribed and the circle are going to be the same. For an outside one, that could be the apothem if we did a circumscribed polygon. So this is just one method of trying to calculate pi and get an idea of what is the relationship. Okay, now I'm going to show a grid square or a grid paper method in this next part, and that's going to give away that you could do this with students. Of course, this is a good example to put up on the smart board or the projector, whatever you have, and demonstrate it that way, but I'm going to show an example with grid paper that the students can do, and you can actually provide several round objects in the class, so that way nobody's copying off each other. Put them in groups to work with and have round objects with different diameters. Okay, this is going to be a little unsteady because I'm off the tripod, but what I did is I just took a can out of my pantry. Serrano's just seemed like a good size can to use for this example. And I have a piece of grid paper. Now this grid paper I measured out ahead of time, and of course usually the label is going to be on it. But this grid paper is 4 squares to an inch, okay, as far as length goes. So each of these squares is a 1/4 inch square. Alright, I would have liked to do an example with metric grid paper, and that way the students would also have a chance to use the metric system instead of just using our standard here in the United States of inches and feet and everything else for what they're doing. But I just happen to have some 1/4 inch grid paper on hand. So what I did is I traced around the can, I put it on the grid paper, traced around it, and we have this circle here. And I measured across, and if we go from this point to this point over here, we're at about, if I get the pen to work, we're at about 13.5. And that's our diameter. So of course our radius is going to be what? Our radius is going to be half that. Well, of course half of 13 is going to be 6.5. We have the 0.5, so we have a radius of 6.75. Now this is what I would do with the students. I'm not going to go in depth, but give you a general idea. The first thing I would do is have them count the number of complete squares. So they could start in like an upper corner and say, okay, well that's a complete, so that's 1, 2, 3, 4, 5, 6, 7, 8. You get the idea. And they could put dots in it, they could do whatever, completely color them in, maybe with a colored pencil. But we have like 8 complete ones there where none of it looks like it's being cut off. And have them do that for all of this. Well, we know that each of these is a 1/4 inch square. So we're going to know the area of the complete squares just by counting those complete squares. So that's going to get us close. Then what you do is you have them look at ones like here where this corner is cut off and try to find a matching part where it looks like there's only this much of a square inside the circle. Okay? So they can look around and say, well, you know, over here this part looks like about the same as this, so if I combine this one and this one over here, that's going to be 1. And so another tick mark as far as how many complete squares they have. Okay, of course with larger objects this would be more accurate, but it's also going to be more time consuming. This is just a casual way of them finding the relationship between the area and the radius, and we're actually going to look at another method here in a moment. But if they know how many square inches this circle is, and we know what the radius is, okay, then we can start to find out, okay, well the area is the radius, or you know, we've got the radius, we came up with a number that's close to pi and everything, and they're going to eventually find that the area is going to be equal to pi times the radius squared. Okay, and in the next section we're going to look at how they would come up with something close to pi times radius squared without getting too exact. Okay, but this would be a good exercise for them to do, or especially even for younger students, maybe pre-geometry, just to get them introduced to the concept. Okay, so I had just told you that we're going to use another method for determining that the area is pi times the radius squared. Okay, and what we're going to use is the fact that we know the radius. Okay, so I have a circle that is already pre-measured into 16 different parts, and I'll stop the camera in between because I'm going to be doing some cutting. But what I would do is give the students a template like this. I would have them use some scissors very carefully and tell them first cut it into fourths. Okay, get the circle cut into fourths. See if there's a way that we can start to determine what is the area of the circle. Okay, so we divided the circle into 4 parts. Now here's the problem. If you ask the students if they could find the area of this circle after we've divided it into 4 parts, they're probably still going to say no. And I put it on this background so that you can see the white paper better than if I had it on the other papers, because this doesn't look like anything they know. It has a straight edge, it has a curve, another radius curve, another radius curved, another straight edge. So this isn't going to help too much. This doesn't resemble anything that we've taught them up to this point. So this is the time when you say, you know what, go ahead and cut these even further. Cut each one of these sections into 4 pieces so that we have 16 equal parts, and then rearrange it and see if we have anything that looks close to a shape that we're familiar with that we could possibly find the area of. So I'm going to pause the tape again and go ahead and cut those up. Okay, so for the sake of time we skipped, instead of cutting the circle into eighths and then asking the students what it looked like, and and they could say, well, if it's cut into eighths and arranged, up down pattern, it begins to resemble a rectangle. What we did is we went ahead and skipped and cut it into 16ths. When we cut it into 16ths, well, it does resemble a parallelogram. Okay, it's not exactly a rectangle, but depending on the age level of the students you're working with, you may get different answers. Now, we know from parallelograms that what can we do? Well, I can take this one here, this last wedge, and I can cut this in half and move half of it over here, and what do I have? Then I have something that resembles a rectangle. But a parallelogram is pretty easy too, because how do we calculate the area? Well, the area is going to be the height, okay, so our vertical height times our length, which is going to be the distance from this corner to this corner over here. So here's the trick for the kids. What is going to be the length of this? Okay, well, if you think about it, what do we really have? We have these radius arcs up here, okay, and if you count, of course, there's 8 of them. Well, we know that we cut this into 16 pieces. So if I have 8 of these arcs going across, isn't that just half the circumference? Okay, and we know from earlier in this video that the circumference was what? Pi times the diameter. Well, if I take half of pi times the diameter, what is that going to be? Well, half a diameter is a radius. So our length going across is going to be pi times the radius. It's going to be half of the circumference. Now the height is going to be what? Well, each of these goes from the center of the circle out to the outer edge, out to the circumference. Well, what is that? That's a radius. So our height is just going to be the radius. So this parallelogram, we can get a pretty close approximation of the area, again, not exact, by just doing pi times r, which is pi times radius squared. Now that does give us an exact, but if they were to actually measure across, because of the radiuses, because we're not dealing with flat surfaces, our area would be just a little bit off. Okay, but this demonstrates it to them. Half the circumference is going to be pi times r, and the distance, the vertical distance from the center to the outside part, if I was to drop a straight line, is going to be r, and so therefore area of our circle is going to be pi times the radius squared.